everyone at the weekly CTP PAS colloquium. Today we have a pleasure to host Nick Ormrod, who finished his PhD at Oxford last September, right? Who freshly finished his PhD with Jonathan Barrett, and now he's a young postdoc at the Perimeter Institute in Canada, working with Rob Speckens and Lucien Harding. And today, Nick will present us a talk on how events can emerge from causation. Nick, the ground is yours.
Thanks very much. Yeah, so thanks very much for having me here for listening. It's a real pleasure to be here. Yeah, so today I'm going to talk about ultimately a new interpretation of quantum theory that Jonathan Barrett and I have put forward. And according to this interpretation of quantum theory, causation is a bit different to how we normally think about it. It plays a different and much more fundamental role. So on this way of thinking about quantum theory, causal structure is actually fundamental, and events emerge from it. So that's the idea I'm going to be explaining. Now, before we get on to that, though, I want to talk a little bit about why we need an interpretation of quantum theory in the first place. And so I'm going to talk about the measurement problem. And the measurement problem is really a cluster of a bunch of different related problems. It means different things to different people, and different people will emphasize different aspects of it. So I'm not going to attempt to give a unbiased, comprehensive account of all the different aspects of the measurement problem and the different ways of thinking about it. Instead, I'm going to start with an unapologetically biased summary of the measurement problem. So this is the way that I would prefer to think about it, although it's very much inspired by this paper by Jonathan. I would really recommend it. Okay, so here's the measurement problem. Unlike most physical theories, quantum theory, as it is standardly formulated, crucially depends on such concepts as observers and measurements, right? You'll find these words in the axioms of the theory, typically. Plays a very important fundamental role. And you might ask, well, what's the problem with, right? What's the problem with quantum theory relying fundamentally on concepts like observers and measurements? After all, isn't physics all about measurement, right? Isn't it all about predicting and explaining the things we observe? Well, one problem that you might have with these concepts playing a fundamental role is you might think that even if we want to predict and explain what we observe, we want to be able to do so in terms of concepts that are themselves independent of observation, right? You might think that physics is about just trying to describe the world independently of our perception of it. You might think that, but you might not. And actually, I don't think that's the most fundamental issue with quantum theory relying on these concepts. I would say that more fundamentally than anthropocentricity, the problem here is the problem of vagueness, right? The concept of an observer, the concept of a measurement, these are vague concepts. They don't have the level of precision that we would normally expect from an idea that plays a crucial role in fundamental physics. Because it's not clear exactly what kind of system counts as an observer, right? I'm pretty sure that I count and that all of you count. Probably my dog counts as well. But I'm less clear on whether a bacterium should count as an observer. Even less clear on whether a virus should count as an observer. I'm not sure about ChatGPT, whether that counts as an observer. It's just not clear. And it's true that, you know, it's a clear enough concept that we can use it meaningfully in everyday conversation, right? Or even in the context of doing a physics experiment. But it's just much less clear and precise than we would normally expect from a concept that plays a fundamental role in physics. I mean, compare it to the concept of a particle in Hamiltonian particle mechanics, right? That's a very well-defined, very kind of precise idea, unlike the concept of observer. And of course, it's the same with the concept of a measurement, right? There are some interactions that definitely count as measurements, like the kind of measurements that we as scientists actually deliberately perform. But it also seems like in some weaker sense, just about any kind of interaction between two objects is counted as a kind of measurement. And so it's not clear exactly what a measurement is. And that's a problem. If part of the axioms of your theory are, you know, this completely different dynamical rule, this collapse rule takes over when you perform a measurement, but you're not clear on exactly what a measurement is, then you're not clear exactly what your theory is saying, right? There's a vagueness at the bottom of your theory. And you might just say, okay, there is vagueness at the heart of quantum theory, there is vagueness in the axioms, but we just have to put up with it. But I think that we can and should try to do better. And if you agree with me that the measurement problem is fundamentally a problem of vagueness, then it seems that solving the measurement problem is necessarily going to involve reformulating quantum theory so that it no longer rests on vague concepts. And I really want to emphasize this point because sometimes it seems that when people talk about an interpretation of quantum theory, they think of an interpretation as being kind of a vague thing, you know, just a couple of ideas that you've got that help you sort of intuitively make sense of the formalism. That's not what I mean when I talk about interpreting quantum theory, right? I don't just mean taking the theory and then saying a couple of sentences about what the theory means. What I mean is actually reformulating the theory. So an interpretation to me, it's not something separate to the theory, it's actually just a better and more precise theory. That's the idea. Now, there have been various attempted solutions to the measurement problem, various proposals for interpretations of quantum theory. Most famous are probably the kind of big three interpretations, right? There's the Everettian many worlds interpretation of quantum theory. There's the de Broglie pilot wave theory, and there's the GRW objective collapse theory, right? Those are the kind of the most famous. But although each of these has attracted considerable interest, none of them has managed to command consensus, right? None of these interpretations have reached the status of majority opinion amongst physicists, even though the newest one of them, objective collapses, is already like 40 or 50 years old, right? So they've been a while and people still don't accept them. And perhaps the reason for this is straightforward. Perhaps the reason why none has commanded consensus is just that none of these interpretations so far are satisfactory. If we assume that none of the interpretations of quantum theory that have been proposed so far are good enough, then it seems that a genuinely satisfactory solution to the measurement problem is really going to require some kind of radical transformation in our concept, some kind of crazy idea that so far has been difficult for us to articulate. Because if it didn't require such a radical transformation in our concepts, we would have come up with it already. Okay, so if you want to try to propose a solution to the measurement problem, if you want to try to develop a new interpretation of quantum theory, I think you have to have some kind of proposal for what this radical transformation in our concepts is likely to be. And mine and John's proposal for what this radical transformation is that causation is fundamental and events emerge from it. That's the basic idea. And I'm going to be trying to make this idea more precise over the course of this talk. But before making it precise, let me just start with an intuition for what it might mean for events to emerge from causal influence. So here's an intuitive assumption. The idea is that if an event happens, it should matter that it happens, right? It should somehow make a difference. You know, an example of an event would be a tsunami, right? And a tsunami definitely matters because a tsunami makes a difference, right? It brings about a flood. It changes other things in the universe. And the idea is that all events should have this property, right? All events should make some kind of difference in reality. They should all have some kind of causal power, if you think about it that way. If an event happens, it should matter that it happens, but it should not matter whether or not the event has been observed. Maybe this second assumption is more controversial, especially if you're familiar with quantum theory. But the idea here is that if the event is part of the objective fabric of reality, then you should be able to check that that event has happened without causing a disturbance. So you see, if you take these two assumptions together, it seems that for an event to happen, it needs to strike a kind of causal balance, right? The fact that the event happens leads to a causal influence, that's this first bullet point. But on the other hand, the fact of the event being measured shouldn't lead to an influence, that's the second point. And so this is kind of the intuition that I want to start with when it comes to making sense of this idea that causation is fundamental and events emerge from it. The idea is you start with a causal structure, you look to see where this kind of causal balance is struck, and that's when an event happens. That's going to be the idea. Now, as I said a second ago, for a solution to the measurement problem or for an interpretation of quantum theory to be plausible, it's going to have to require some kind of radical idea that we haven't been able to make sense of so far. And I think the reason why we haven't been able to make sense of this idea so far is that for most of the history of quantum theory, we haven't really been paying close attention to what causation means in quantum theory. But in recent years in quantum foundations, that has changed. Causation has become a real hot topic, right? There have been a lot of papers come out on causation over the last 10, 15 years. And in particular, there's been a lot of work on causal modeling in quantum theory. And that line of research in particular, quantum causal modeling, has forced us to get clear and precise on exactly what causation means in quantum theory in the first place. And it's really going to be using that kind of analysis of causation that we get from quantum causal models that I'm going to try to make sense of this idea. So now that we're on quantum causal models has furnished us with a precise analysis of causation in quantum theory, I think we're now in a position to make sense of this vague idea and to make it more precise. So in this talk, that's what I'm going to do. I'm going to try to show how we can develop this idea of events emerging from causal influence into a precise observer-independent reformulation of quantum theory. That is, into an interpretation of quantum theory that solves a measurement problem. And so to do that, we're going to proceed in two different parts. In part one, before we get on to the whole business of trying to interpret quantum theory, we're just going to ask a much more down-to-earth question, which is, what is causal influence in the first place? And I'm going to propose an answer to that question that's very much based on the recent work on causal modeling. And then after we've got clear on what causal influence is in the first place, in part two, we'll come to the question of how we can take advantage of that analysis in order to answer this question of how events emerge from causation. And it's going to proceed by formalizing that intuition that I've just been developing. All right. So let's get into it. What is causal influence in quantum theory? Now, to answer this question, I will start by considering a very simple operational scenario. And in this scenario, I'm assuming that some unitary transformation U gets implemented on a system, some fixed unitary transformation. We know that that unitary transformation takes place. And now I'm going to bring a couple of agents into the picture. So before U is implemented, Alice down here has the opportunity to implement a Hamiltonian that I'm going to call M. And then after U is implemented, Bob can intervene on the system, and he can measure some observable that I'm going to call N. And of course, we can ask a question, which is, can Alice signal to Bob using this protocol, right? Does Alice applying her Hamiltonian before the unitary is implemented make any difference to the statistics for the measurement that Bob will do after U is implemented? Can Alice signal to Bob? And when it comes to defining causation, the idea is simply going to be that we're going to say that the operator M influences the operator N through this unitary channel U, if and only if Alice can signal to Bob. Right? So the idea is that you've got causation if the Hamiltonian changes the observable, at least if you're thinking about it in the Heisenberg picture. And if you remember Heisenberg's equation of motion, that tells us that the rate of change of an observable induced by a Hamiltonian is proportional to the commutator of the operators. And so that gives us this formal definition for causation. Right? So M is our Hamiltonian, U to the minus 1 of N, that's the version of this operator, whoops, that's the version of this operator that gets rolled back through the unitary transformation view onto Alice's Hilbert space. That's our definition of causation. So we've got the idea that causation is about a Hamiltonian changing an observable, but when we define causation in this way, we can also note that there's an equivalent way of thinking about it, a distinct but ultimately equivalent definition. And that's that if we suppose that Alice instead measures the observable M before U is implemented, then again Bob's outcome statistics will be changed when he measures M. Right? And that's just a simple reflection of the fact that when two observables don't commute, they're not commeasurable. So here's our definition of causation between a couple of permission operators. It's easy to extend that to causal influence between sets of such operators. So simply we'll say that there's causal influence from this set to this set, if and only if there exists a pair of operators, one from each set, that influence each other. And similarly, we can also define causal influence between systems, because a system can be thought of as a set of operators, right? A system can be thought of as the set of all of the local operators on the system. And so we'll say that the system A influences the system B, if and only if there's a local operator on A that influences a local operator on B. And that's it for causation in quantum theory. There's a little cheat sheet here. So we've got these different but equivalent ways of defining causal influence between a couple of permission operators, and we've just seen that this naturally gives rise to a definition of causation between systems. Yeah.
I interrupt quickly. I have a
Yeah.
very stupid question. If you go back 2 slides to your sort of diagram.
This one?
Yeah. So this kind of makes sense to me mostly, except that it I feel like there should be some dependence on the state that Alice is given, right?
Oh,
If
great
Alice is
question.
given some state, which is
Great
not state of this guy, then she's still not going to do anything.
Yeah. No, that's a thank you.
That's important.
Yeah, that's a good point. Yeah, so indeed, you see that I've not plugged in any particular quantum state to the bottom. This is deliberate. So the idea when I talk about Alice being able to signal to Bob, what I really mean by that is that there exists at least one quantum state that our system could start with, such that if we do start with that state, then Alice is able to signal to Bob.
Okay.
So what I'm implicitly doing, yes, is quantifying over all possible infinite states. Essentially, what we want from our analysis of causation is we want causation to be a property of the dynamics, right? The intuition is that two things influence each other if they're dynamically connected to one another, and so we want the question of whether two things influence each other to be settled just by the dynamics. So in this case, just by the unitary transformation, which is why we quantify over all states. Any other questions about causal influence in quantum theory? Does this make sense?
Initial state is not only caused by dynamics. It's kind of you have to prepare the first state, and then so there is some ambiguity in.
So interestingly enough, later on in the talk, I'm actually going to explain how it is that you might think a state is prepared by dynamics. We're going to talk about events emerging from dynamics, and we're going to understand the state in terms of the kind of emergence of events. For now, though, given that we're just defining causation in terms of standard quantum theory,
is this whole construction non-relativistic, or could it be made relativistic?
yeah. So I guess so far there's nothing relativistic going on. We're just doing standard non-relativistic quantum mechanics. Ultimately, on the approach to quantum theory that I'm going to develop, at the core of it is a kind of causal structure, and the form of the causal structure is a bit similar to the kind of light cone structure that we have in general relativity, in the sense that it forms a partial ordering. So that's going to be how this approach interfaces with relativity theory. Yeah, but maybe I'll come back to that a bit later. Okay.
remembering the happy children. We are using the language which is not familiar to me. Although the explanation, I don't know how to implement it.
We cannot hear anything, and maybe we move it until the end of the talk. Nick, please continue.
Okay.
There's some technical problems.
Us to write on chat.
Yeah, maybe please write on the chat, and we will ask it at the end of the talk. There's some problem with the microphone.
With your microphone.
Okay, Nick, please continue.
Cool. Okay. So there we have causal influence in quantum theory. So we're done with part one, and now we come on to
In classical causal modeling, we usually see that two variables are connected by dynamics, and when we say that one variable is cause of another variable, we can statistically record an effect. How do you draw parallel between these two? What is cause and what is effect here? Everything is operators you are calling.
So in Judeo-Pearl classical causal modeling, causes and effects are both variables, right? We talk about one variable causing another. Here, we're just replacing variables with operators, essentially. Now one operator causes another. In Judeo-Pearl classical causal modeling, the relation of causation is given by functional dependence, right? Because dynamics are given by functions classically, so you're just asking, does this variable depend on this variable in the function? Here, we're replacing the idea of functional dependence with unitary dependence, which is defined in terms of this commutator expression. Yeah. Okay, so now that we've got this analysis of causation, we can start to investigate how it is that events might emerge from it. And remember from earlier, we're going to be, the sort of key guiding assumption or guiding intuition is going to be that an event emerges when two things happen, right? When a system is not affected by measurements of the event, but it is affected by whether or not the event happens. So I said before that we can think about this as a kind of causal balance. And so now what I'm going to do is I'm going to give you a formal definition of causal balance. So I'm going to assume from now on that events are represented by a projector, right? In quantum theory, an event is a projector. It's an assumption I'm making. And so here's how we define what it means for a projector to be causally balanced. So given that we've got this kind of unitary transformation on a pair of systems A and B, we say that a local projector on A, PA, we say that a local projector PA is causally balanced relative to B if both of these two conditions are met. So let's take these two conditions apart. First of all, we're requiring that there is not too much influence. Or what I mean by that is just that the projector itself does not influence B. Remember how we were defining causal influences between sets of operators, right? We defined it just in terms of whether or not there are operators in the set that influence each other. So what this condition tells you is that PA does not influence any of the local operators on B. And remember, there were a couple of equivalent ways of thinking about causal influence, but one of them was about measurements of the cause, disturbing or not disturbing measurements of the effect. And so what this first condition, but not too much influence, tells you is that if Alice measures the projector PA before the unitary is implemented, this won't make any difference that Bob can detect after the unitary is implemented. And so not too much influence is a formalization of this first intuition, right? That the system, in this case B, should not be affected by measurements of the event.
But if you take this formal definition of influence by U, a unitary transformation, yes, that means that PA should commute with U of U to minus 1 of B. Yes?
That's right.
Okay. So it means that this particular projector should be a spectral projector set for any operator from B, or U to minus 1 of B.
I didn't catch that last thing.
Okay, because, when does projector commute with a Hermitian operator?
Yes.
Okay.
Mm-hmm.
So it must be one of the
Oh, I see. Yes, absolutely.
projection
Absolutely.
of its eigenvector. Okay.
Yeah.
So it means that all these observables which characterize B somehow should have the common eigenvector, which is displayed at PA.
That's right. That's right.
Okay.
Yeah.
It's like a special.
Yeah, it's a very special. I mean, another way of thinking about it is this statement is equivalent to the statement that PA, if you map it through the unitary channel, it's just going to end up on A again, right? It's not going to go to B at all. Indeed, it's a special situation. So the second condition is that we've got enough influence, where I've got a slightly more complicated statement here. So now I'm saying that for any permission operator, local operator on A, NA, if NA doesn't commute with PA, then NA does exert an influence on B. So what's the intuition there?
Can I actually repeat the previous question done by Professor Bill?
Pardon, maybe we shift it until the end of the talk. We have already quite a lot of questions, so maybe we let the talk and then we start discussion afterwards.
Okay. So the intuition here is that if NA is able to change PA, then it should be able to change something along B. So if you want to think about it really operationally, right, the idea is that if Alice, before the unitary is implemented, implements some Hamiltonian that changes PA, then there's always a measurement that Bob can do after the unitary to detect evidence of Alice having done that, right? So that means that Bob really knows about the degree of freedom that's encoded by this projector PA, right? And that's encoding our second assumption, right? Because remember, the idea here is that PA is going to end up representing an event. And we want the event to be, we want our system, in this case B, to be affected by whether or not that event happens. So any change to the event leads to a causal influence on the system. So there we have it, causal balance. We want not too much influence because we want to not be influenced by measurements of the event, but we want enough influence because we do want to be influenced by anything that changes the event. Good. So now that I've given you that definition of causal balance, I can now give you a theorem. The event theorem says that the full set of projectors on A that are causally balanced relative to B is commutative, and more than being commutative, it forms a Boolean algebra of projectors. So what I mean by a Boolean algebra of projectors is that you got this Boolean algebra where the conjunctions are given by matrix products of projectors. Disjunctions are given by taking the sum minus the product, and so on. The statement that's always true in a Boolean algebra, which is something you need, is given by the identity operator, right? That's always causally balanced. The statement that's always false is given by the zero operator. That's also always causally balanced. So we always get this structure when we check for the causally balanced projectors. We always get the Boolean algebra. And remember that Boolean algebras are exactly the kind of structure that we use to represent classical event spaces. At least in the case of finite cardinality. And so, this event theorem is good news for the idea that events emerge from causal balance, right? Because these causally balanced projectors are forming exactly the sort of structure that we expect an event space to form. Now, in case all of this sounds a little bit abstract, let's try to bring it back down to earth with an example. But I think the C0 transformation is really the simplest but still vaguely interesting example of causal balance. So in a C0, the definition is here, right? You've got intuitively a C0 is a transformation where if A is prepared in the zero state, then nothing happens to B, right? You've got the identity. But on the other hand, if A is prepared in the one state, then you've got the X gate, which is the X Pauli matrix, right? The not gate being applied to B. And so that's why it's called a controlled not, right? Controlled on the computational basis degree of freedom on A, either nothing or the X gate will get applied to B. And it's a coherent control of unitaries because the C0 is a unitary channel. So since we've got this unitary channel, and since I've told you what the two conditions that define causal balance are, we can now simply check what are the local projectors on A that are causally balanced relative to B. And a little bit of working out tells us that this is the full set of projectors. So we've got the zero projector and the identity. And actually, we always get those, no matter what unitary transformation we're looking at, so that's not very special. But in the case of the C0, we also get something more interesting. We also get these computational basis projectors being causally balanced. And you can check that this whole set of projectors forms a Boolean algebra. It forms an event space, as the event theory requires. Now, I'm not going to get into sort of really rigorous proofs of these projectors being causally balanced, but just to give you a kind of sense of how you might convince yourself this. The not too much influence condition, that requires that all of these local operators on A commute with all the local operators on B in the Heisenberg picture. But you can kind of see that the computational basis projectors actually just commute with the C0 case itself, which means that these local operators on A before the unitary, that is the local computational basis projectors on A before the unitary, they're just going to get mapped straight up through the unitary and land up here. And so necessarily they're going to commute with all the operators over here. So that's how you can see that all of these operators satisfy the not too much influence condition. And then for the enough influence condition, that's kind of intuitively suggested just by the definition of the C0 that I've got over here. Right, remember the idea of the C0 is that what happens to B is controlled on the computational basis degree of freedom on A. So it's probably not hard for you to believe that any Hamiltonian on A that changes the computational basis projectors is going to lead to a on B. So there we have it. We get this event space of computational basis projectors when we check for causal balance in the C0 transformation.
Sorry to ask, so it seems that you need that the gate, that the unitary that each of the structure is entangling, because if it was product, you won't satisfy this enough influence, right?
Excellent, yeah, excellent point. Yeah, so yes, so a unitary being entangling is actually equivalent to there being causal influence between the two systems. And so if your unitary was not entangling, if it was just a product, then you would never be able to satisfy this enough influence condition unless the antecedent condition was not satisfied. So unless the trivial is. So that's why in that case of a product unitary, the only causally balanced projectors would just be the identity transformation, sorry, the identity operator and the zero operator. Yeah, good point. Yeah, so and again, this reinforces that what we're looking for here is really a causal balance. The problem with a product unitary is that there's not too much causal. Sorry, is that there's not enough influence between the systems. If you imagine a swamp gate, there would be too much influence between the systems. But a C0 kind of gets it just right. Good. So I think it's useful to take stock of where we are at this point. We introduced the idea that events emerge from causal balance. And we've seen, I think, encouragingly, that causally balanced projectors form event spaces. That was the event theorem. But so far, we are yet to take this idea and turn it into a theory. Right? We've not got the interpretation of quantum mechanics that I promised you to begin with. So now our challenge is whether we can take these ideas and turn them into a precise physical theory, capable of making predictions for any quantum experiment. And here's the key for how we do this. So far, we've only defined causal balance in the context of individual unitary transformations. And there's not very much interesting physics you can model with a single unitary transformation. Experiments typically involve a bunch of different things going on. So to develop a theory, the key is to extend the idea of causal balance from individual unitary transformations to full-blown circuits of unitary transformations. It's not too hard to do this. So think of an arbitrary circuit. I've got an example on the board. I'm going to define a bubble as being just any set of individual systems, any set of individual wires in the circuit. So my example of bubble here is the one of B, C, F, and K. Now I want to define what it means for some projector on one of these systems to strike a causal balance relative to the bubble as a whole. And here's going to be the approach. So I'm going to define a future balance projector as one that's causally balanced relative to the combination of all systems in its future within the bubble. That's a bit of a mouthful. Let me just talk about an example. Look at this system C, right? Ask yourself how many systems are in the future of C within the bubble. There's two, right? Because there's F here and there's K here. So a future balance projector is causally balanced relative to the combination of all systems in its future. So in this case, a future balance projector on C is going to be causally balanced relative to the combination of F and K.
Why not L? Yeah, why not L?
Because I'm defining causal balance relative to a bubble, and I'm considering the bubble B, C, F, and K.
Okay.
So if we look at that bubble, then we would be including that. And defining causal balance relative to the combination of F and K is not too difficult. What we do is we just take the union of all the operators on F and all the operators on K. And remember, we know how to define causal influence between arbitrary sets of operators. So we're going to be able to define causal balance with respect to that set, no problem. So we can define causal balance relative to the future of C, future balance projectors, and the event theorem is going to tell us that we get some event space of future balance projectors. So that's what this E up C relative to the bubble B means. It's the future balance event space. And similarly, we can define past balance projectors. So our notion of causal influence, because it's given in terms of the commutator, is symmetric in time. So we can define causal influences into the past as well as into the future. And just in the same way that we define future balance, we can define past balance. So for example, if you take F and you look at the systems in its past within the bubble, we have C and B. And so this is going to be the definition of a past balance projector on F. And so you see, I decorated the systems in my bubble, each with two event spaces of projectors, because we've always got future balance one and a past balance one. So in general, if you've got a bubble of n systems, we get two n event spaces that are causally balanced. And this is what I mean by causal balance relative to a bubble. There's two ways of being causally balanced relative to a bubble. You can be future balance or past balance. Good. So now that I've shown you how you can derive this whole set of event spaces from causal structure within a bubble, we can now ask the question of whether there's a natural way of attributing a joint probability distribution over all of those events, right? And in quantum theory, we often don't get natural probability distributions, but the probability theorem tells us that we will get them as long as we derive projectors from causal balance. So some of you might be familiar with the framework of consistent histories. One way of saying the probability theorem is that the causally balanced projectors within a bubble always generate a set of consistent histories. But if you're not familiar with consistent histories, don't worry. All you need to know is that this expression defines a probability distribution. So in general, in quantum theory, this kind of expression where you just line up projectors in a row and trace them, that doesn't always give you probabilities because it does not even always give you positive numbers, right? It can give you negative numbers, complex numbers. But it just so happens that whenever you derive the projectors from causal balance, you do get a probability distribution. That's what the probability theorem says. And this gives us all the ingredients that we need to propose an interpretation of quantum theory, right? Because we know now, given a circuit, how I can derive sets of causally balanced projectors for each bubble. And we also know how to give them probabilities. And so there's an obvious kind of theory that you can write down at this point. So the theory of causal balance is our interpretation of quantum theory. It says that reality consists of a unitary circuit and the events that probabilistically emerge from it via causal balance relative to each bubble in the circuit. The probabilities for a set of events to emerge relative to a given bubble are given by this expression, which we know gives us probabilities because of the probability theorem. And that's it. That's the theory. Yeah, so just to briefly mention a couple of points about this theory that are important to appreciate, particularly because they're quite radical, they might be quite unfamiliar. One goes back to this question that a couple of people asked earlier about what is the role of the initial state, right? You'll see that for us, reality consists of a unitary circuit and events. I've made no mention of the state in the theory. Even though we use unitary circuits and unitary transformations in the theory of causal balance, the point of those transformations is not that you're going to plug in some initial state at the bottom and then see what that state evolves to. That's not the point of the circuit. The only point of the circuit is to kind of give birth to these events via this idea of causal balance. As hopefully we can see in a second, if I've got time, we can make sense of the idea of using the state in quantum theory, but the state does not provide us a description of the universe. There's no such thing as the quantum state of the universe on this approach to quantum theory. So that's one thing that's unfamiliar about the theory of causal balance. It's the way that we kind of the state loses its fundamental role, and instead it's just the causal structure that plays a fundamental role. And another thing that's unusual about it is this kind of relationalism. So there was a question earlier about, why isn't L included, right? And the answer to that question was, well, because we were talking about a bubble that doesn't include L. On this interpretation, you can consider the events that happen relative to any bubble in the circuit, and different events can happen relative to different bubbles. So there's quite a radical relationalism there. The reason why we can call this an interpretation of quantum theory is because of this completeness theorem. It tells us that any experiment that can be modeled using standard quantum theory can be modeled using the theory of causal balance, and we reproduce the same statistics. Now I need to wrap up, but hopefully I can very quickly give you a sense of how we would use our theory to model a very simple experiment in quantum theory. So really the simplest kind of thing that you can do in physics, I guess, is prepare a system, transform it, and measure it, right? So consider this prepare measure experiment described for now in the language of standard quantum theory, right? We just prepare a qubit in a computational basis, say, apply a unitary transformation, and then we measure again in the computational basis. How do we model this experiment using the bubble theory, or that's just another name for the theory of causal balance? Well, my claim to you is that this circuit is a model of the prepare measure experiment. So how does that work? Well, let's look at this bubble, B, C, F, and K. We can do some calculations to figure out what the causally balanced event spaces are. And it's particularly interesting to look at this event space and this event space. So the PAS balance event space on C, it's PAS balance, and it emerges as a result of its interaction with B, right? So it emerges as a result of this first C-naught transformation. And we get these computational basis events happening. And so it's these events that we're going to identify with the idea of preparing our system in the state I, right? That's the first step in the prepare measure experiment. Up here, when we look at the future balance event space, we also get computational basis protectors. And we're going to identify these with the outcome of our computational basis measurement. Right? So we've got preparing the state at the bottom here, transforming over here, obviously, and then we've got measuring at the end of the experiment. And to check this works out, we need to make sure that we get the probabilities that we expect from standard quantum theory. So remember, we've got that lineup and trace rule for calculating probabilities in the theory of causal balance. I'm not going to go into the calculation right now, but you can calculate that type of probability distribution, and then you can calculate a conditional probability for one of these events to happen, given that one of these events happen. And you find that you get this Born rule mod squared expression that you expect from standard quantum theory. So indeed, we recover the statistics that we expect. Yeah, I'm almost done, but I guess there's a little bit of time just to talk about another, maybe slightly more exciting application of this theory, which is to model valid equality violations. Valid equality violations are generally thought to demand some kind of non-locality in order to explain them. But we have a model that explains valid equality violations at least without any non-local causal influences, right? Remember that our whole approach is based on the precise notion of causal influence. And you can see here that there's no way that there's going to be a causal influence from any of the systems over here to any of the systems over here. right? Because the dynamics are what are product dynamics. So the idea of this model is that we've got the preparation of the entangled state down here, Alex's measurement here, and Bob's measurement here. And I'm going to breeze through this because we already saw an example before. And by similar arguments, when we take the bubble that's denoted by all of the red lines, we find we get a pass balanced event space over here, which includes projectors onto entangled state. So that's going to be the way that we prepare our entangled state that we're going to use to violate Bell inequalities. We find that we get computational basis projectors over here that correspond to balance setting. We get computational basis projectors over here that corresponds to our outcome. And again, as always, we can calculate joint probabilities for the events within this bubble by doing our lineup and trace projector expression. And we find we get exactly the statistics that we expect from quantum theory. And so, of course, they violate Bell inequalities. And so the upshot is that if we sort of reconfigure our causal concepts in this way, we say that causation is actually fundamental and events emerge out of causation, rather than saying that events are fundamental and causation is just a relation between events, then it turns out that we don't need non-local causal influences in order to explain Bell inequality violations. Good. Okay. So now I can basically wrap up. There's another cheat sheet here which just summarizes this sort of story with emergent events. We define causal balance in a unitary transformation, extended it to causal balance in circuit. We had a nice theorem that told us that when we derive causally balanced event space within a circuit, they always generate set consistent histories, or equivalently, they always give us this kind of nice probability formula. And that gave us all the ingredients that we needed in order to formulate this theory of causal balance, which in essence says that reality is just a circuit plus the events that emerge from it probabilistically in accordance with this probability rule. There was also a completeness theorem, which told us that the theory of causal balance can reproduce any quantum statistics. That's why I think it's fair to say that it's an interpretation of quantum theory. And of course, and I didn't point it out explicitly at the time, but if you cast your mind back to that slide where I defined the theory of causal balance, there of course was no mention of the observer or of measurements or anything like this. And remembering the discussion of the measurement problem from the beginning of this talk, right? I said that solving the measurement problem just involves reformulating quantum theory in a precise way without relying on vague concepts like the observer or like measurement. And yes, so by that standard, I think the theory of causal balance does count, at least as a proposal for a solution to the measurement problem. Yeah, and we also saw a couple of examples, including how we can apply this theory to explain Bell inequality violations without any causal non-locality. So that's it. I'll wrap up there then, I guess. Thank you.
Thank you very much for very interesting talk. So I open the discussion and I suggest that we start with the question of Professor Fizyki, which is on the chat, which we could not hear because of the microphone problems. Cool.
Vocabulary used here doesn't seem to correspond to standard formalism of quantum mechanics. Hamiltonian is the Hermitian operator which acts on the state vector. Therefore, what is the meaning of a term implementing Hamiltonian by observer? But there are it associates with this Professor Joukowski actually, and the question of Professor Birula, perhaps it means that the observer acts on the system during the time with the unitary operator explanation minus IHT.
Maybe we go one question by a time. Okay. Maybe the first.
Yeah. So I'm not sure I quite got that first question.
What does it mean that the observer, since you are using, if I understood correctly,
yeah,
maybe that we take a look at this question.
Yeah, maybe if I could.
Which one? The vocabulary used here does not seem to correspond to standard formulation of quantum mechanics. The Hamiltonian is a Hermitian operator which acts on the vectors. Therefore, what is the meaning of the term implementing the Hamiltonian by the observer?
Yeah, I'm not sure. I mean, it seems to me that it's,
The vocabulary does not seem to correspond to the standard formulation. I think it corresponds to the standard formulation.
yeah, I mean, I think implementing a Hamiltonian is a standard concept. It just means that you're applying a unitary transformation on your system that's generated by running a Hamiltonian for a particular amount of time. Yeah. That's the idea.
So maybe Michał.
Okay, I have two quick questions. So one is to what extent, I guess your circuits, or let's call it circuits, they give you the causal structure. To what extent you have a freedom of choosing those bubbles you talk about as you
Right.
or are you constrained somehow? That's the first question. The second is, what if you had replaced the unitary transformations by maybe channels? Would it affect the definition?
Good, yeah.
Or, okay, the last, like, okay, like, can you go to POVM, can you generalize it to POVMs as opposed, because you seem to be sort of, just, you seem to represent projective measurements, or like, you effectively in the first one.
Okay, all three very good questions there. So first of all, are you constrained in any way in the bubbles that you choose? So the answer is according to the theory that I described on this slide, you're not constrained at all. So relative to each bubble, that really means like every single bubble in the circuit is equally legitimate, and you can talk about events emerging from it. Something that's worth noting is that most of the bubbles are, in any circuit, most of the bubbles are kind of boring, right? So for example, well, for one extreme example of a bubble that's boring, if you include all of the systems in the bubble, then there's always going to be too much influence for any causal balance to emerge, so you don't get anything. If you take any one of the bubbles where there's just one system, then there's never enough influence for anything to emerge. And so it's only quite special, like you can choose any bubble and you can calculate what event spaces emerge, but generally speaking, even for quite contrived circuits, it's only going to be a limited set of bubbles relative to which anything interesting happens. That having been said, it is still a very radical thing to say, that you're completely unconstrained, that you've got events happening relative to each bubble, and completely different things can happen relative to different bubbles. And this, I think, is the biggest kind of problem that's fixed by the theory of causal balance. Like, if you're going to not be satisfied by something in the theory of causal balance, it's probably going to be this kind of radical relationalism. There are some no-go theorems that push us to some kind of relationalism in quantum theory. No-go theorems relating to extended versions of the bigger spread scenario. I don't know if these ring a bell. So definitely it seems like we need some kind of relationalism in our theory, but you might think, do we really need the relationalism to be this radical? And currently John and I are interested in seeing whether we can tame the relationalism in any way, but that's still ongoing. So the second question was about channels rather than unitaries. It really does matter that we're talking about unitaries. So if we go back to the definition of causation, we defined it in terms of commutator in the Heisenberg picture. And taking the commutator in the Heisenberg picture, it doesn't really work when you're talking about non-unitary channels, because somehow it sort of doesn't really make sense to transform operators through the transformations in the same way.
I mean, one direction it does.
Indeed, in one direction it does.
You can always transform to the future. Yeah.
Yeah,
you can always you can formulate that probably instead of pushing back, pulling back. You can push it forward.
Yeah, that's a very good point. Okay, yeah. So we could just
the M measurement or M Hamiltonian, and then like Michał says, you can use the channel because it is in one direction. You know that it will work.
Okay, yes. So good. So you would be able, okay, here's what would happen if we were trying to tell this whole story with unitary channels. We would be able to write down a similar definition of causation, but just instead we'd be applying U to M rather than U minus 1 to N. So that would be fine. And then defining causal balance, I guess this whole thing is still going to work with that modified definition of causation. But the bit where it's going to go wrong is when we extend the circuit, we'll be able to define the future balance projectors. But I think we're probably going to get an issue when we try to define past balance projectors. That will have to be checked. But yeah, my intuition is that something is going to go wrong because the kind of time symmetry of the unitary channels, I think, are very important in this approach. But yeah, having said that, it's something that I guess needs to be checked. So yeah, thank you. And when it comes to POVM, so that was another good question. We talked about, we find causal balance in terms of projectors, but I could instead have replaced this PA with an O, right? I could define it in terms of arbitrary observables on A. And I would have got a closely related theorem to the event theorem. The theorem just would have told me that, you know, if an operator is if an observable is causally balanced, then it's going to be something whose spectrum is given by the projectors that are causally balanced. So the projectors in this Boolean algebra. Okay, but that still isn't directly answering your question. When it comes to incorporated POVMs, the way that I think about it is this. So the fact that they get this event theorem, the fact that the causally balanced projectors or even causally balanced observables are kind of just generated by this Boolean algebra, and the Boolean algebra is an event space. For me, that's very suggestive of the idea that events are projectors and observables just represent information about which projectors have happened. Now, of course, operationally in quantum theory, we can do POVM measurements, right, that aren't PVMs. And so we need to be able to explain how those measurements take place. And essentially, in our interpretation, it's going to be a church to the larger Hilbert space situation. It's always a PVM on a larger system will be the idea. Good.
Okay, I think Mark, you show this transparency when you show that your results are the same as in standard interpretation of mechanics, quantum mechanics. When you show that the reality is such a causal circuit. Could you show it?
This one?
No.
Or this
no, like yes,
yes,
probably yes. And
Okay.
then that's this preferred measurement.
Yeah.
Then you show this result at the previous stage of the next stage of this transparency. This result. Okay, and next one goes to the next one. Okay, and then you calculated something. Okay,
Yes.
and this is probability of what in your language?
Right. So for us, you know, the theory says that reality is a circuit. So in this case, reality is this circuit plus the events that emerge from it relative to each bubble. So that includes the events that emerge relative to this bubble, B, C, F, and K. And so we're going to get one event from each, or we're going to get an event from each of these 8 event spaces getting selected. So one of these, really one of these computational basis projectors is going to get selected from the event space. And that's going to be one of the events that happens.
Okay.
But a priori, when I look at this, I don't know which one will get selected. It could be this one, it could be this one. And that probability expression with the lining up and tracing projectors, that is what enables me to calculate the joint probabilities for any given collection of events to happen.
So the way to have some probability, and how do you check against, I would say, experiment, whether it is true or not? By measurement.
Yeah. That's right.
And what is this measurement then?
Well, this is the process of measurement.
Okay.
I mean, it's measurement on this approach is treated in a way that's analogous to how measurement is treated in, you know, Newtonian mechanics, right?
Yeah, sure. Because
Yeah.
formally I understand, but finally you have to measure.
Yes.
Okay, to check this probability against the reality. Okay. So you have to measure.
I agree.
Avoid something like measurement in your on all.
Well, there's an important subtlety there. So certainly your theory needs to be able to explain and predict why you should expect to see some particular thing when you do a measurement. So if your theory of physics doesn't have anything to say about measurement, I completely agree with you. That is a pretty devastating problem. But it doesn't follow that the concept of measurement has to be a part of the axioms of your theory. It is in quantum theory, but it isn't in Newtonian mechanics. And Newtonian mechanics doesn't have a problem with measurement. The idea here is that this theory is like Newtonian mechanics in the sense that measurement doesn't play a role in the axioms, but nonetheless we can talk about measurements, and this is how we talk about them.
Okay, Thornton, I think we should finish, and Nick is with us here until the end of the week, so everyone is welcome to talk to Nick. Thank you very much again.